So we just got done looking at the brute force algorithm, which is going to be a way to solve a traveling salesman problem that will guarantee to find us the optimal solution, which is going to be the Hamilton circuit of least total weight. However, we saw that the brute force algorithm also is classified as an inefficient algorithm because the amount of effort it's going to take to solve a traveling salesman problem grows disproportionately to the size of the problem. So for instance, if I just have 6 vertices in my graph, you're going to have to find 60 different possible Hamilton circuit weights. So that's already going past the ability for us to kind of like solve that on a quiz or test in this course, and it very quickly, for the number of vertices, grows past the ability of even our fastest supercomputers to be able to solve. So this leads us on the hunt for an efficient algorithm. So that'll be an algorithm that the computational effort needed to carry it out is going to be reasonable given the scope of the problem. Now here's going to be, unfortunately, the trade-off. Efficient algorithms, at so far, what anybody's been able to find, only produce what is known as an approximate solution. An approximate solution is going to be a Hamilton circuit that most of the time produces a weight that is reasonably close to the optimal solution. Now, if you noticed kind of all of the wishy-washy wording in this, that's a pretty good observation. Most of the time, what does that mean? Well, sometimes this approximate solution could actually be maybe even the worst weight to her. Right? And then we hope also that it's reasonably close. So both of these are kind of our hopes or our goals for this approximate solution. But here's the thing, unless we're willing to put in the time to employ the brute force algorithm to actually find that optimal solution, we won't even know how close we are. And we don't even know necessarily how much, what percentage of the time our solution is going to be close to the optimal solution, and what percentage of the time we're just like maybe looking at some of the worst possible cases. We have no idea. But the trade-off for these approximate solutions is we're going to be able to find them fairly efficiently. So let's take a look at our first algorithm that's going to produce these approximate solutions, which is called the nearest neighbor algorithm. Alright, so the nearest neighbor algorithm, let's go ahead and record the steps and then we'll see it applied to an example. So for the first step, we're going to represent the problem with a complete weighted graph. Right, so once we have our complete weighted graph, you're then going to start at the designated vertex. So for most traveling salesman's problems, for whatever the traveler is, he's going to have a home base, and in the problems that we're going to be solving in this course, that home base is going to be identified for you. So for step 1, start where you're supposed to start. So for step 3, of all the edges attached to the starting vertex, you're going to choose the edge that has the smallest weight. So then you're going to travel along that edge to the second vertex, which you're going to hear me call that second vertex is, I'm going to refer it to as the nearest neighbor. of that starting vertex. Okay, so for the next step, you're just going to keep going to the nearest neighbor, for whatever vertex you're at, as long as you don't visit a vertex you have already been to. Because on a Hamilton circuit, you are not allowed to repeatedly travel to a vertex. So you're just going to keep doing this nearest neighbor, and then the last step is after you have visited all the vertices, you're going to return to your starting vertex. Now keep in mind, every vertex has a connection to every other vertex because you're looking at a complete graph. So there's going to be an edge for you to return to your starting vertex. So you're going to return to the starting vertex to close the circuit. So I like to word this as you're just going to go home. Let's take a look at these steps in action on this problem that we were looking at previously. Okay, so we're going to find an approximate solution to this traveling salesman's problem. We're going to write the weights in the order found, and we are going to start and end at vertex A. So maybe I'm going to use a different color down here. So let's do the same thing in nearest neighbor. I'm going to start here at vertex A. So out of A, I've got 3 different edges. The least total weight to get out of A is 15. Now here's what I mean when I say write the weights in the order found. This is how I check your work to see that you're using the algorithm properly. I'm going to travel from A on this edge of 15 to vertex D. I would highly suggest that you record the weight at the same time you record what vertex you're going to go to. So we're going to go from A to D. I like to mark it on my graph so I can see it, and I'm going to record the weight down here. Now I'm sitting here at D. Out of the 2 edges to get out of D, 12 or 9, 9 would be the least total weight. So the nearest neighbor for D would be vertex B. I'm going to mark the edge to show where I went. I'm going to record my weight, and I'll record the vertex I went to. Now at this point in time, I only have one other vertex that I haven't been to yet. So we'll go to that one. So C, which gives me a weight of 30. And then now I've been to all different vertices in the graph, so now we'll come back home to vertex A and grab that edge of 43. This is the weights in the order found based upon what the nearest neighbor algorithm tells me where I can go to first, second, and etc. Okay, so for nearest neighbor, this is actually going to be the circuit, and then the weight of this tour, if we were to add all these up, is 97. So this is what it means when it says the weights in the order found. Notice out of all of the different possible circuits here, because we did brute force on this one and we did actually list all of the different Hamilton circuits, notice that the circuit we found was actually the worst option. And that's the trade-off with the nearest neighbor algorithm, is that we were able to get through it very fast, very efficiently, but we only get what's called an approximate solution. There's no guarantee we're actually going to find that optimal solution. Now also as a heads up, these would be the weights in the order found, but in terms of the final answer, I would also accept, actually I'll leave this in the same color, I would also accept the mirror image of this. So A, C, B, D, A. Okay, so I need you to list the weights in the order found, but in terms of the actual route then, we could go this route or we could travel in reverse order and we're still going to hit this weight. Now technically I would normally leave it like this, just because this is also not only the weights in the order found from the algorithm, but the vertices specified in the order from the algorithm. But you might see, for instance, on a multiple choice question, maybe this mirror image version of this.